Hi, good morning or afternoon or evening, depending upon when you're watching this. For me, it's the afternoon. So welcome to our 13th lecture of Math 1B03. In today's lecture, we're going to finish up section 2.2, which looked at invertible matrices, and then we're going to start section 2.3 on the characterization of invertible matrices. And we'll carry on this lecture into the next lecture. Now, last time, what I gave was a procedure to find the inverse of a matrix. In particular, what I showed first, what we first did was define what the inverse of a matrix is. That is, given a matrix, the inverse is a matrix that we could find that multiply the original matrix by to get to the identity. And we gave a procedure to find that. And our goal today is kind of twofold. We're going to first introduce elementary matrices to justify why this procedure works. And the other thing that we're going to do is we're going to look at some characterizations of invertible matrices. So by this, I mean other ways to look at a matrix, do operations on your matrix to decide whether an inverse exists without actually using the complete procedure. And over here is a little comic. Hopefully it's funny. I don't know, it's some lame math humor, but maybe you'll enjoy it. Okay, so make my face disappear there, and let's talk about elementary matrices. So we're going to start with a bit of an observation, okay, which you may or may not have seen. So going back to kind of section 1.1 and 1.2, we learned about our elementary row operations. So here I have a matrix, and let's say I do a row operation. Here's my row operation, and I'm going to do one of the simple ones. I'm going to multiply row 2 by 6. So row 2 multiplied by 6 gives me the new matrix 2, 3, 1, 6, 0, 24, and 0, 1, 0. So that gives me an elementary row operation. Now the interesting thing is that this row operation here is the same as a matrix multiplication. So this is the same as taking the matrix 1, 0, 0, 0, 6, 0, 0, 0, 1 and multiplying it by my matrix 2, 3, 1, 1, 0, 4, 0, 1, 0. And when I do that, I multiply everything out, I get 2, 3, 1, 6, 0, 24, and 0, 1, 0. So what we're seeing here is this row operation that we performed on the matrix is somehow being captured in this matrix over here. And in fact, if you stare at it for a second, it's if we ignored this matrix A here and we put the identity matrix and then applied the row operation multiply row 2 by 6, this is the matrix that we would get. So let's make this a little bit more precise about what's going on here. So we're going to introduce some terminology. A matrix E is an elementary matrix if it can be formed from the identity by a single row operation. So the example that I had above is an example of an elementary matrix. All right, and let's just make this explicit. 1, 0, 0, 0, 6, 0, 0, 0, 1. So you should think about this. What row operation did I perform to the identity to get this? Well, what I did is I did row 2 of I3 multiplied by 6. Okay. What about some of the other elementary row operations? Well, one of the other elementary row operations is swapping. So this matrix here is an elementary matrix because it's formed from the identity by swapping rows 2 and 3. Swap rows 2 and 3 of the identity. So these are both examples of the identity matrix. This corresponds to multiplying a row by a constant. This corresponds to swapping rows. And then let's do the other elementary row operation where you can take a multiple of one row and add it to another. So I could have something like this. So 1, 0, 5, 0, 1, 0, 0, 0, 1. So how did I get this? The way I got this was I add 5 times row 3 plus row 1 of the identity matrix of size 3. So each of these matrices that I've written on this page here are an example of an elementary matrix, and you can do make lots of these yourself. Okay. Oh, and let me do another example here to kind of show you something else that's happening. And this will kind of motivate what we're going to be doing kind of in the next part of this lecture. So let's go back to my matrix, or a new matrix, 1, 2, 3, 1, 0, 1, 1, 0, 2. And what I want to do is I want to take row 3 times 5 plus row 1. That's a valid row operation. And if I were to do that, I would get, let's see, 5 plus 1, so I would get 6 up here. 5 times 0 plus 2 is 2. 5 times 2 is 10, plus 3 is 13, and I'm not changing the rest of the matrix. So this is my valid row operation, but this is going to be the same as taking the matrix 1, 0, 5, 0, 1, 0, 0, 0, 1. This is an elementary matrix, and in fact, it's just this elementary matrix up above, multiplied by the original matrix, so 1, 2, 3, 1, 0, 1, 1, 0, 2, and you get 6, 2, 13, 1, 0, 1, 1, 0, 2. Okay, so what you should be hopefully seeing and maybe making a guess about what's happening is all of those elementary operations that we learned back in section 1.1 and section 1.2 correspond to first doing a corresponding change on the identity matrix, like what we've done here. So this would have been a row operation. Then instead of doing the row operation, we do the row operation on the identity matrix, and then we multiply this new matrix by the original matrix, and that gives you a matrix that corresponds to doing the row operation. So what we're really trying to get at here is that each of these row operations that we do on a matrix, each single one can be represented by a matrix multiplication with an elementary matrix, okay? And that's actually what I've written over here. Each elementary row operation can be represented by multiplication by an elementary matrix. And this is great because if we want to explicitly keep track of row operations, we can think of it as a series of matrix multiplications. And we're going to be using that fact when we prove that the procedure from last class is true. So we'll stop here and I'll see you in the next part.